Alright, work through for the second class. We're going to talk about descriptive statistics. So, I already wrote this down. Question 1. Mr. Vomit Bucket has found the following data on error rates. So these would be participant who made 10 errors, participant who made 15 errors, etc. Of course, you would require context, but the fun thing about a lot of statistics is you can run certain stats without knowing anything about the numbers that you're looking at, which is also very alarming. Now, having said that, first question here is, what is the mean? Well, the mean we can't just see. We have to actually compute that. The advantage, though, is that you already know how to do this. I think everyone has learned this at the very latest in high school. Symbol is an M for mean, or X bar for a sample, or if this were a whole population, mu, which is a Greek letter. And the formula for this is pretty simple. You take all the observations, the sum of all the observations, this is x1, x2, x3, all the way to xn, in this case 7x7. I sum them all up and I divide by the total number of observations. Well, I just said 1, 2, 3, 4, 5, 6, 7 total number of observations. So how would I compute this? I know that you can already do this. 10 plus 15 plus ... plus 11. This plus this plus this plus this plus this plus this divided by n. And what you should have found then is 14. Now, what I want to impinge upon you is look at the data. People don't do that. Is 14 a reasonable number? Well, this is below 14. Above it, little bit, pretty far above it, below it, above it, below it. That looks pretty reasonable to me. I sometimes get students who put something wrong in their calculator and they find something like this and then they say, I didn't find the answer you did. No, of course not. Is this a reasonable mean for this distribution? No, it isn't. Ask yourself why it's not. Every number in this distribution is 20 or fewer. The mean of these numbers can never be 140, okay? Or 21, or 25, or 10,000. It's not possible. It can also not be 0.5, unless I would have many super small numbers, but I don't. We have calculators, and that's good. But calculators do what you tell them to do, and if you make a mistake, your calculator will not tell you. So it is your responsibility as a sensible researcher, academic, whatever you are, to make sure that what you have is reasonable. Okay, but I should not have erased that. Okay, I'm just going to put this in again. What do we have? 10, 15, 20, 11, 12, 19, 11. Okay. Question 2. What is the median of the data set presented in question 1? Median. Okay, median, what was that again? The middle observation, the number that has that has 50% of observations below it and 50% of observations above it. Now here's what I see on exams. Okay, so I want you to pay close attention because there will be a question like this on the exam and many people get it wrong. Middle observation. Okay, how many observations do I have? 1, 2, 3, 4, 5, 6, 7. Okay, then the middle one has 3 below, 3 above. And then what I see people do is this. 1, 2, 3. Okay, 1, 2, 3. Okay, this is the median. Wrong. The median is the middle observation once all observations have been sorted. Don't forget it. How do I sort it? It's very easy. I look for the lowest number, that's 10, then the next one, that's 11, and the next one, that's 12, and the next one, that's 15, 19, 20, 2, 3, 4, 5, 6. No, I missed one. What did I miss? 11. Did I miss another 11? I did miss another 11. See, this is the danger of this. Okay, let's try that again. I had another 11. That was this one. Sorry about that. Then I had 12, 15, 19, to save it. Yes, I count in Dutch. Cope with it. Okay, 2, 3, 4, 5, 6, 7. These are sorted. And what's the middle number now? Well, as you can see, the middle number is actually 12. This is the median. Why is it the median? Because it has, in this case, 3 numbers below it and 3 numbers above it. It is the middle observation. Once numbers are sorted, don't forget it. Okay. Question 3. What is the mode of the data set presented in question 1? Well, mode is something completely different. I don't have any more colored markers, so I have to do this. I'll do this one in blue. What is the mode? The observation that occurs most often. And what is that? I have one of these, 2 of those, one of these, one of these, one of these, one of these. So, this. The mode is 11, because it occurred twice. What if I'd only had one 11? Well then, every number occurs once, and when every number occurs once, there is no mode. It's just, we mathematically would say it's undefined. It does not exist in that case. But we did not have that situation, so we do not have to worry. Alright, we're going to get into slightly more difficult stuff now. Still the same data set, still should not have removed it. Start again. Okay, I am going to write it down in organized fashion again. We had a 10, we had 2 11s, we had a 12, I think, we had a 15, we had a 19, and we had a 20. Okay. Compute the first and third quartiles for the data set presented in question 1. Okay, why are you going to do something with quartiles? Again, you have to sort the data set. So this is the data set from question 1, but now sorted, low to high. If you were to do high to low, you get the same results. Same thing for the median. Think about it, it doesn't matter whether you go this way or that way. Right, middle is middle. Okay, now I already know this is the median, and although not asked about it, let's make a mental note of it anyway. Now how do you find the first and third quartiles? Well, you have to find the positions, and you use to compute those positions, you just look at these 2 bits of data. So the data points below the median and the data points above the median. Okay, and then the process is quite simple. I have 1, 2, 3 observations here. So then I say 3 to find that quartile, right? I'm looking for the first quartile, Q sub 1. I say, okay, I have 3 observations, and then to use my formula, I add 1 and I divide by 2. And this yields 4 divided by 2 is 2. And then I know that on this position is the first quartile. Okay, this is the first position, second position, third position, second position. This is Q sub 1. This is the median. We give that symbol MD. Now I need to do the same thing here because I also need that third quartile. How do I get the third quartile? Well, actually in a very similar way. How many observations do I have above the median? 3 again. 3 plus 1 divided by 2 is 4 over 2 is 2. Okay, of these 3 observations, higher than the median, this is position 1, this is position 2, this is position 3. And I was looking for position 2. Q sub 3, the third quartile. Okay, now at this point, what I can do, can I? I think I can. Let's do this in steps of 2. 20, 18, 16, 14, 12, 10, 8, 6, 4, 2, 0. I think I have everything. Do I? Yeah, I think so. Let's do a box and whisker plot. One of the contributions from the great John Tukey, the statistician. Okay, I make a box, and I have in that box the median, which we know is 12. The first quartile is 11. Well, this is 10, so about halfway through that. This is drawn by hand. It's not going to be perfect, right? And the third quartile, that's the top of the box, that's 19. Okay. What else goes in a box and whisker plot? The lowest and the highest value. Well, the lowest value is 10. I put that in like this. That's the whisker. And he has another whisker. The highest value, well, that's actually 20. Now I have a box and whisker plot. And this is a very useful plot when you're exploring data because it shows you the middle point of the data, the median, the first quartile, the third quartile, the highest value and the lowest value. Pretty good. Because these whiskers are so small, I immediately know all my data points are pretty tight. They're close together. Okay. All right. Now we're going to actually compute stuff that's difficult. Difficult when you first see it. And I promise you now, by the end of this course, variances, standard deviations, with your eyes closed. And then you say, I wish I was back in the day when I just had to do variances because now I'm doing analysis of variance and I have like 10 formulas for everything. But we're not there yet. Calm down. It's going to be okay. Okay, I'm going to write down some stuff. I just want to see how much space I have in the camera. Okay, that's my X. I have 10, 11, 11, 12, 10, 11, 11, 12. I want to give myself some space. I'm going to write a little small, 15, 19, 20. Same data sets as before. Okay, now, what am I going to do? The question is compute the variance for the data set presented in question 1. Okay, let's start off with the definitional formula. The definitional formula makes it clear what you're doing, hence definitional. It is, however, computationally pretty intense. So let's just quiet. Let's just get started. Okay. So what is my formula? My formula is sigma, small sigma, equals, and then I say I take the sum of every observation minus the mean squared divided by big N. Later we're going to see you can also divide by big N minus 1, but for now, don't worry about that. We're going to treat this as if it's a whole population. Don't worry about it. This is all we need to do for now. Okay, how am I going to do that? Well, it's fairly simple as long as I know what the mean is. I need the mean. So what I like to do in these cases is first make a grocery list. I call it a grocery list. And the grocery list has everything I need. So I have this sigma, I have that formula. And what else do I need? Do I have a little bit of space left? I can barely see. Okay. I'm going to write down x bar, which was 14. We computed this. This was question 1. 14 is the mean of this data set. Okay, now I need to do this somewhat scary looking formula. But I think we can do that. Okay, what does the formula tell me? Calm down. Look at what the formula says to you. I'm going to sum something. Okay. I'm going to take every observation, subtract its mean, and square it. Okay. And then I divide by big N. Okay. So what is the first x? Well, each x is an observation. So the first x must be the first observation. That's 10. Okay, 10 minus 14. And I square it. This part of the formula is now covered. But it tells me to sum something. Oh, that means I have to do this for every single observation. Okay, well, I can do that too. Plus 11 minus 14 squared plus another 11 minus 14 squared plus 12 minus 14 squared plus 15 minus 14 squared plus... I'm running out of space, so I'm just going to put in There's ellipses there, just that, but I have to do this plus 19. Yeah, it's just not going to fit. Plus 19 minus 14 squared plus the final one, 20. Minus 14, it's really tight here, squared. Okay, and I divide that by big N. Well, that's the total number of observations. 1, 2, 3, 4, 5, 6, 7. 7, yes. Okay, I can do this. Now, write everything out. When you do this by hand, don't skip any steps. Write down every step because it's very error prone. Okay, now what do we get? Let's do a couple just for the sake of time, but you should compute all these terms. Okay, what's the first one? 10 minus 14. Well, that's minus 4 squared plus 11 minus 14. We can still do that. 11 minus 14 is minus 3 squared. And I'm going to skip a couple, but you do this for every single term and end up with plus 20 minus 14, well, that's 6 squared. Okay, now I go through these. I now have 7 of these terms to square, different scores to square. Okay, minus 4 squared, that's 16, plus minus 3 squared, well, that's going to be 9, plus dot dot dot, plus 6 squared, that's 36. And let's not forget to divide. Okay, divide by big N. When I do this, I'm just looking at my answer here to make sure I get all the numbers. Okay, when you add up all these numbers, you should get 100 divided by 7, and that is 14.29. This is the variance of that data set. Now, what I would like to introduce here, because this is going to come in really handy later in the course, and if you're watching this video, you're doing the right thing, you're making all the effort, so you're going to jump a little bit ahead of some of the others. As you can see, this is pretty intense because I have to compute all kinds of different scores, and you will find, especially when you have a lot of a mean that has decimal points, this gets very messy because you have to keep subtracting something with decimal points and then squared and you get decimals. It's a hassle. So let me show you a very clever shortcut. This formula if you use a little bit of algebra, can be rewritten. It can be rewritten into something that we call the computational formula. And the computational formula, that looks like this. Sum of x squared minus sum of x squared divided by n divided by n. Now, this looks a little weird because you divide by n again. This is nothing to be afraid of. I just do a division here, subtract that from this number, and I do a division there. What I need, though, is an x squared and the sum of x's squared. Okay. Now, that means I need to compute something, but you will then see this is much faster. And this gives you the same answer as the previous definitional formula. Okay. Now, I wrote down these numbers, and I'm going to tell you what they are. The first thing I need is sum of x squared. Well, what that means is I take all the x's, observations, I square them, and then I add them all up. That's what this says. I take the sum of all squared x's. Okay, well, the sum, I'm just seeing what I wrote down. The sum of all these x's is 98. See if you can replicate that number. 10 plus 11 plus 11 plus 12 plus 15 plus 19 plus 20 is 98. Okay. Now, what else do we need? Well, the formula asks for the sum of all squared x's. Okay, that is something a little different. So, I'm going to write this down here. I have the sum of all x's squared, and I have the sum of all x's squared. Now I know this looks super confusing, and you may think that the sum of all x's squared and the sum of all x's squared is the same thing, but it's not. What's the difference? This thing, the sum of all squared x's, simply asks you to square every observation and then add them up. So, for example, I would get 10 squared, 11 squared, 11 squared, 12 squared, 15 squared, 19 squared, 20 squared. And the sum of, oh, that's really hideous, sorry. The sum of all those numbers is the sum of all x's squared. Notice where I put the pause. The sum of all x's squared. The sum of all x's squared. But this is the sum of all x's squared. This number, sum of all x's squared, is 1,472. Again, compute it. 10 squared plus 11 squared plus 11 squared plus 12 squared all the way down to plus 20 squared. Okay. But this is the sum of all x's squared. And that is the same as 98 squared, which equals to 9,604. The sum of all x's, the sum of all x's squared. This number. Okay. Now that sounded like a very long explanation, but once you've done this a couple times, this becomes second nature. And now look at how easy it is to compute a variance. Remember what we did before. 10 minus 14 squared plus 11 minus 14 squared plus 11 minus 14. Imagine that you have 100 observations. You would have to compute 100 deviation scores. But with this formula, what I say is sigma equals the sum of all x's squared, 1,472, minus the sum of all x's squared, 9,604, divided by big N, well that was 7, and then the whole thing divided by 7 again. And when you do this, this also takes a little bit of, there's some steps, right? You first compute this, you subtract that number from this, and then you divide the outcome of that by 7. And what you should get is exactly the same, 14.29, exactly the same thing we got before. Try it. Try this in your calculator, see if you get that. Now you have seen not only the definitional formula, but also the computational formula. And although computational sounds like it's more work, it's actually the other way around. The computational formula is less work than the definitional formula. Okay, now I've given you a small data set. 1, 4. I clearly need to change these markers, by the way. 1, 4, 5, and 9. And the question is, compute the standard deviation. What's the standard deviation? Square root of the variance. Okay, so I can use the same thing all over again. I need sigma. Well, let's make a grocery list. If I'm going to need sigma, what is the first thing I need? The mean. Okay, the mean I have computed is 4.75. You know how. Add up these 4 numbers, divide them by 4. 4.75. And I'm going to do sigma. And if I were you, I would do both formulas just to get that practice in. Okay, I have sigma x minus x bar squared divided by big N. Or I can use that computational formula. But let's first do this. Sigma in this case would be the first value, 1 minus 4.75 squared plus 4 minus 4.75 squared plus 5 minus 4.75 squared plus 9 minus 4.75 squared. Okay, I realize now that in the previous part I used the symbol sigma. I should have used sigma squared. That's the variance. In this case, I'm using sigma, which is, like I said, the square root of the variance. So I should not forget to take the square root. Okay, now here you start to see, if you do this on a calculator, how much work this is. It's a lot of work to deal with numbers with a fraction in it, where you compute all these deviation scores. So why don't we try that other formula, 1, 4, 5, 9. These are the x's, and what did I need again? Sum of x, sum of all x's squared, and sum of all x's squared. Okay. Well, the sum of all x's is 19. The sum of all x's squared, remember, that would be 1 square is 1, 4 square, 16, 5 square, 25, 9 square, 36. I add up these numbers and I get 123. This is the sum of all x's squared. Sum of all x's squared. Okay. And then here I have the sum of all x's squared. Okay. So that would be 1 plus 4 plus 5 plus 9. 19 squared. I like to put that in there. There's 19 squared, so you see again where this comes from. Alright? And now I use my formula. Okay, well that was the sum of all x's squared minus the sum of all x's squared divided by big N, and the whole thing divided by big N. And the square root out of that, because I'm dealing with standard deviation. Okay, well, sum of all x's squared, 123 minus 361 divided by 4 divided by 4 square rooted. Now, if you get a little confused, you have these two numbers and you don't know which one goes where, the biggest one always goes here. Okay? Maybe that helps. And if I do this, then I get 2.86. Oh, sounds pretty good. That looks to me like it could be right. Right? The mean is 4.75. I have some bigger values, I have some smaller values. I think that standard deviation looks about right. Okay, so I know that in class we have focused on the definitional formula. That's to hammer the concept home. We have not yet spent much time on this, but we will later. You're just getting a little bit ahead if you start to also use this formula. That's all I have for now. Let me know if this was useful, and if any questions arise, just tell me.